Today's supersonic aircraft required years of research and development before they took their first flight. Scientists and engineers working to break the bonds of the technology of the day to create aircraft that fly higher, faster, safer, and more efficiently than the aircraft that came before. Each time learning and building on their successes and failures. From the X-1 to the X-31, X-planes have been the proving ground for today's aerospace technology. It all began with X-plane research. This is the Grumman X-29, an advanced technology demonstrator aircraft.
Edwards Tower, Grumman 2, 268.1, radio check please, over. 29455, we got you lost.
The X-29 has thin supercritical carbon composite wings that sweep forward at a 30-degree angle. Air moving over the forward-swept wing tends to flow inward rather than outward, allowing the wingtips to remain unstalled at high angles of attack and therefore easier to control in extreme maneuvers. The X-29 wings provide less drag, more lift, better maneuverability, and more efficient cruising speeds. Metal forward-swept wings were pioneered by the Germans in 1944 with the Junkers Ju-287 and later in the Hansa 320 business jet. These wings would break if the aircraft exceeded Mach 0.6. It was the advent of aeroelastically tailored carbon composite wings explored by Dr. Norris Krohn that made the X-29 possible.
So that's really the driving force behind the X-29. The fact that with composite materials, one can design the structure of a wing in such a way to counter that adverse twist that occurs when the wing deflects due to an air load. The ability to do that and prove that you could do that to a confidence level that would be acceptable was the fundamental reason for building the X-29.
The X-29 has close-coupled variable incidence canards. Located forward of the wing, the canards can move up and down 40 times a second to control and direct airflow to the wings and to affect the pitch of the aircraft. Strakes extend along the rear fuselage from the wing to the exhaust nozzle of the aircraft. These strakes are equipped with flaps that augment the canards for pitch control. The X-29 program was funded by Grumman, the Air Force, DARPA, and NASA. Glenn Speight, Grumman's former project engineer for the X-29 program.
We've talked about the technologies on the X-29, the wing, the canard, the instability, the three control surfaces. Integrating all those technologies was perhaps the most difficult part of the X-29. To make sure that we never stalled the canard, which would cause us to lose control of the aircraft, to make sure that we optimally configured the wing and the canard so that the technologies worked together and did not fight one another, really was the challenge of the X-29 program, and implementing a flight control system that could control an airplane as unstable as the X-29 was the most difficult technical task that we had to overcome.
On August 27, 1984, the first X-29 rolled out at Grumman's Calverton plant. On December 14, 1984, the X-29 made its first flight. the late Chuck Sewell, Grumman test pilot for the first flight of the X-29.
Okay, going up in the power. Stand by. 10, 9, 8, 6, 5, 4, 3, 2, 1. Right delay. Here we go, guys. 70% knot. 80. 90. Everything looks good. Temperatures are good. 153 seconds to go here. 63 back. Airborne, 157.
The X-29 reached a planned altitude of 15,000 feet and a speed of Mach 0.43 during its first flight.
In fact, the whole airplane had no discrepancies. As far as I'm concerned, the airplane could be refueled, turned around, and we could go in a few minutes. It's that good.
Kurt Schrader, chief test pilot at Grumman Aerospace.
The X-29 has a very specific mission, and that is to demonstrate the technologies that are incorporated into the airplane. And the pilot's purpose in this is, in the whole program, is like a pilot in any program, and that is to see how the airplane flies and then evaluate potential missions for types of airplanes that the technologies could be incorporated into, and define whether or not those handling qualities are applicable and satisfactory for that mission. The airplane is an absolute delight to fly, and it flies just exactly what you'd like a fighter airplane to fly like, and the only time you're aware of the forward swept wing is if you happen to peer out the window.
It's very unlikely in the near future that we'll see either a commercial or a military aircraft that looks identical to the X-29. But the technologies in the X-29, the canard, the fly-by-wire flight control system, the aeroelastic tailoring of the composites in its wing, and perhaps even the forward-swept wing itself, will eventually find application on military aircraft and perhaps commercial aircraft as well, for the simple reason that they enhance the efficiency of the aircraft, they reduce the fuel consumption, and make the aircraft of the future more affordable to own and to operate.
In 1943, the design community in this country thought we could build an airplane that would go up to or exceed the speed of sound. We began to accomplish designs at Wright Field. These were just preliminary design. The man behind the scene at that time was Ezra Kocher, who was an engineer in the engineering division at Wright Field. Our idea was then to build an airplane that would be simple, because problems had already occurred in airplanes where, nearing the speed of sound, they approached what we called compressibility. And in that compressibility, there's certain flight control characteristics showed up that made it very difficult to control the airplane.
It all started with Bell Aircraft's XS-1, better known as the X-1, the first aircraft to safely exceed the speed of sound. Its mission was to investigate the possibility of manned supersonic flight. The test program, which had 157 flights, was designed to safely explore transonic speeds while examining structural and physiological phenomena. Fueled by supercooled liquid oxygen and diluted ethyl alcohol, the XLR-11 rocket engine was capable of producing 6,000 pounds of thrust. The X-1 was loaded into the bomb bay of the B-29 bomber to be carried aloft to its launch altitude. This procedure saved the extra weight of fuel that would be necessary for the aircraft to power itself to the thin, cool air of the stratosphere. On October 14, 1947, Chuck Yeager became the first pilot to fly faster than the speed of sound, Mach 1.06. At 10 in the morning, the B-29 took off from Edwards Air Force Base. While the bomber climbed to altitude, Yeager and the crew of the B-29 reviewed the final checklist in preparation for the launch. When the mothership reached 10,000 feet, Yeager descended from the B-29 by using a specially designed elevator that carried him to the cockpit of the X-1. He had been suffering from 2 broken ribs, which he concealed from the flight surgeon, and he required the use of a shortened broomstick handle to secure the cockpit canopy. At 10:26 a.m., the X-1, nicknamed Glamorous Glennis in tribute to his wife, was dropped over Rogers Dry Lake to begin its assault on the sound barrier.
And they dropped it from the B-29 at about 240 miles at 25,000 feet. Then we fired off the rocket and accelerated out beyond the speed of sound.
Yeager took the X-1 to 45,000 feet. At this altitude, he leveled the aircraft. He now ignited the 3rd rocket cylinder, which provided the thrust to propel the now lighter aircraft past Mach 1. Yeager's supersonic flight lasted 20.5 seconds, nearly twice the duration of the Wright brothers' first powered flight 44 years earlier. It is a tribute to the X-1 program's aeronautical engineers and ground crew that the flight proceeded perfectly. The 14-minute flight established a standard for all future flight testing with the research aircraft that were to follow.
The X-1 series of aircrafts began by designing a profile or a shape which was as simple as possible from what we knew then about aerodynamics. In other words, everything was somewhat symmetrical. The wing was very thin, but it had as much curvature at the top as it did at the bottom. They call that a symmetrical airfoil. The fuselage was more bullet-shaped because the fuselage is round and it has as much curvature on top on the sides as it does on the bottom. This makes possible flight with the fewest problems as we saw it in those days.
On December 12, 1953, Chuck Yeager once again broke the speed record in the Bell X-1A, exceeding Mach 2.4. But the aircraft encountered inertia coupling, a phenomenon caused by rapid changes of aerodynamic and inertia characteristics resulting from an aircraft's configuration. A rolling motion is coupled with a yawing motion, causing the aircraft to go out of control. Fortunately, Yeager was able to recover his aircraft and land safely. Information learned from Yeager's near disaster helped make today's supersonic and hypersonic aircraft controllable. The X-1 was the forerunner of today's supersonic aircraft such as the F-16. And Concorde, the first sustained Mach 2 supersonic commercial transport. Parallel research programs led to the Douglas D-558-2 Skyrocket, the first aircraft to exceed Mach 2. The Skyrocket, as it was known to the program engineers, was loaded in the belly of the Superfortress. The technicians had chilled the alcohol fuel to increase the aircraft's capacity, taped the fuselage panel seams, and coated the D-558-2 with wax to give the aircraft every possible aeronautical advantage. In November 1953, Scott Crossfield became the first pilot to fly twice the speed of sound, reaching an altitude of 83,000 feet. The Skyrocket left the Superfortress, and its rocket engines were ignited. Its modified exhaust nozzles designed to increase the engine's thrust worked perfectly. Leveling off at altitude, Crossfield nosed the aircraft into a shallow dive and edged past Mach 2 at 62,000 feet. The Skyrocket was the first of the rocket planes to incorporate low aspect ratio aft-swept wings. On the 50th anniversary of the Wright brothers' flight, and 6 years after Yeager broke the sound barrier, Crossfield passed the next milestone in the quest for speed and controllability. Scott Crossfield.
The D5582 is one of the research airplane series. It was funded by the Navy. That's the reason it didn't have the X designation. It was primarily to review or look at what the transonic effects of a swept wing would be. And with it, we flew some several hundred flights and wrote the book on how we would design and build modern swept wing airplanes. And it proved many of the things that we have learned since then. The D5582 was a very productive airplane, and almost every airplane in the air today has a little bit of the D5582 basic information or what we learned from it in it.
On September 7, 1956, Captain Ivan Kinchelow flew the Bell X-2 with the objective of achieving a new altitude record. The X-2 was the most complex of the early rocket-propelled experimental aircraft, using a two-chamber Curtiss-Wright engine, giving it 15,000 pounds of thrust. Kinchelow flew the aircraft to a record altitude of 126,200 feet. The swept-wing Bell X-2 was developed and designed to explore flight at speeds and altitudes far beyond those possible with the X-1. But experimental flying is just that. As hard as the engineers and test pilots may work to ensure optimum safety, there is always the possibility of a tragic accident. On September 27, 1956, Captain Milburn Apt, on his first flight in the Bell X-2, became the first pilot to reach Mach 3.2. Within 10 seconds of this historic moment, the aircraft began an uncontrollable divergent roll. Apt fought desperately to regain control of the aircraft. G-forces alternated between +6 and -6. These violent forces knocked Apt unconscious. He never recovered. Both Apt and the X-2 were lost. The X-3 Stiletto, built by Douglas Aircraft, was designed to fly at sustained supersonic speeds above Mach 2. The X-3 pioneered the use of titanium in aircraft airframes and skins. Lacking sufficiently powerful engines, the X-3 was a failure in its original mission. It did, however, provide extensive data on the inertia coupling phenomena, and research results led directly to modifications of the North American F-100 supersonic fighter. Kelly Johnson, director of Lockheed's famed Skunk Works design team, incorporated much of the X-3 design work into the F-104 Mach 2 fighter. The Bell X-5 was the first variable sweep-wing supersonic aircraft. The X-5 was designed to test the aerodynamic feasibility of variable sweep wings in free flight. The wings could be varied from 20 degrees to 60 degrees. Grumman's F-14, known as the Tomcat, is a dramatic illustration of early X-plane research applied to one of today's enduring high-performance fighter aircraft. Paralleling the intense research in the area of supersonic flight, equally intense research was being conducted to explore VTOL, vertical takeoff and landing capabilities. The Ryan X-13 was designed to explore and demonstrate pure jet vertical takeoff and landing for future fighter aircraft. Its legacy is the ability to transition easily and effectively from vertical to horizontal flight by means of an articulated main engine nozzle. Little did the Ryan engineers know that what they proved feasible would make a vital contribution to man's first footsteps on the moon. The Lunar Excursion Module essentially behaved on landing like the X-13. A prime reason for the development of the Bell X-14 was the need to study the pilot's ability to function in the vertical takeoff and landing environment. Bell designed special exhaust nozzles that could be rotated in order to divert engine exhaust down or straight back to maneuver the aircraft. Sir Stanley Hooker made extensive use of the X-14 data in designing the P-1121, predecessor to the Hawker Harrier VTOL fighter attack aircraft. The latest design evolution is the McDonnell Douglas AV-8B Harrier, flying today in the U.S. Marine Corps and Royal Air Force inventory. Although several other fascinating approaches to VTOL research were addressed by Hiller's X-18, the remarkable Curtiss-Wright X-19, and the Bell X-22A, today we know that it was the Bell XV-3 that provided the impetus for further development of the tilt rotor concept. With Army and Air Force sponsorship, the Bell XV-3 first flew in 1955. 22 years later, the initial test flight of the Bell XV-15 took place. Jointly sponsored by NASA and the Army and contracted through Bell, the XV-15 is a pure tilt rotor technology demonstrator. Two 3-blade 25-foot diameter rotors powered by turboshaft engines provide vertical lift and forward thrust to the XV-15, enabling it to fly up to speeds of 340 knots, twice the speed of traditional helicopters. The Bell Boeing V-22 Osprey is a design evolution from the XV-15. The aircraft is fabricated from graphite epoxy composite laminates and incorporates a digital fly-by-wire control system. The larger rotors are 38 feet in diameter. The rotors and wings will fold for compact storage. Capable of multi-mission roles for the 4 armed services, the Osprey will carry up to 24 troops and have a crew of 3. Commercial variations for short-haul routes will be another use for the V-22. This is an exception in the tradition of X-plane research. It is rare that research technologies and configurations are directly incorporated into production aircraft. The rollout ceremony of the #1 Bell Boeing V-22 Osprey production aircraft occurred on May 23, 1988. The most celebrated and productive aircraft in the X series, the X-15. The North American X-15 was the first aircraft capable of leaving the Earth's atmosphere and flying into space. It was designed to fly routinely at altitudes in excess of 250,000 feet and speeds exceeding Mach 6. Scott Crossfield, first test pilot and design contributor to the X-15.
Well, the checkout in the X-15 was rather abrupt in that on our first flight, we flew it as a glider alone. That gave me 3 minutes and 58 seconds to learn how to fly the airplane and bring it in for a landing. On the approach and landing, I had a control problem that really turned out to have a very simple solution, but the airplane, for all intents and purposes, appeared to be unstable in pitch to me, which meant that it was very difficult to control it. And the pitching oscillations got very high, and I had to figure out a way to get the airplane on the ground at the bottom of the pitching oscillations so it wouldn't wrap up in a ball of molten metal.
Harrison Storms, chief of North American's X-15 design team.
The question has been asked probably many times, how come this aircraft could fly both in space and in the atmosphere? That's really quite simple. For in the atmosphere, you have the controls of the vertical and the horizontal tail. This makes it fly like any normal aircraft. When you're out of the atmosphere, up around 100, 200,000 feet, you don't need the wings, the horizontal or the vertical tails. You can fly just purely as a body itself. In order to maneuver it, however, there are reaction controls in the nose of the airplane to pitch it up and down, and also yaw it back and forth, and in the wingtips to roll it right or left. That way, it can maneuver in space as well as it can maneuver in the atmosphere. It has both sets of controls.
On November 15, 1960, Scott Crossfield made the first flight of the number 2 X-15, configured with a 57,000-pound thrust XLR-99 rocket engine. This was the first man-rated throttleable rocket engine. It initially enabled the pilot to control the thrust output of the engine from 50% to 100%. Crossfield, using only 50% of the available thrust, reached a speed of Mach 2.9 on this flight.
I'm reading 320. Large zinc is holding at about 55. Number 1-2, dive brakes showing open. How's it look, Al? Look real good, Scotty. You made about a 10-degree turn to the right when you came off.
The speed brakes in the X-15 vertical stabilizer were activated to help keep the aircraft within the planned flight profile. Bill Dana, NASA Dryden's chief test pilot and the pilot of the last of 199 flights of the X-15.
Well, it was certainly, the X-15 was certainly a more high-performance airplane than anything I flew before or since. Higher accelerations, things happening more quickly, including getting to faster speeds quicker.
Bill Dana describes a typical X-15 flight.
It was about 45 minutes to an hour from takeoff to the launch point. The B-52 did one circle locally here to check out all systems, including telemetry, and then headed uprange into Nevada. The launch point was typically 200 to 270 nautical miles north of here, quite often in the Tonopah area, sometimes at a launch lake about 75 miles north of Las Vegas. You can see frost on the belly of the airplane there, where it froze due to the cryogenics in the tanks. And we also jettisoned some propellants prior to launch to cool down the fuel lines and prevent vapor lock. When you launched, it felt like you were fired off the shackles. You actually fell away at zero gravity, but it felt like you were fired off. But once you got the engine lit, you got the lift back on the airplane and left the launch scene fairly quickly.
The X-15A-2 extended the X-15 program to further explore the performance possibilities of the aircraft. The white ablative coating was designed to protect the X-15A-2 at speeds approaching Mach 8 and at temperatures of 2,400 degrees Fahrenheit. On October 3rd, 1967, Major Pete Knight took the X-15A-2 to Mach 6.7, 4,534 miles per hour, the maximum speed reached by the aircraft. Pete Knight.
Yeah, the X-15A-2 was, of course, a modification of the basic airplane, and it actually made a three-stage vehicle out of it. The B-52 being the first stage, carrying us up to 45,000 feet. The second stage being the external tanks, allowing us to accelerate to Mach 2 and 70,000 feet, at which time we jettisoned the tanks, recovered the tanks by parachute for reusable conditions. And then at that point, we had a full load of internal fuel, which was the third stage, and that would then allow us to go out to Mach 8. The speed flights that I was assigned to in my particular program was the build-up to the maximum Mach number of Mach 8 or Vmax, whatever the airplane could do, and a build-up with this configuration: the external tanks, the ablative material, the window eyelids, the ramjet, assessing the stability of the vehicle, assessing the procedures associated with those kinds of flights. And of course, we were in the process of that build-up program. It just so happens that the program was canceled once we reached 6.7 Mach number.
The 9-year flight test program of the X-15 is still considered a milestone in the experimental research aircraft program. It can safely be said that every high-performance aircraft flying today has benefited in some way from the truly remarkable X-15. The Boeing X-20 Dinosaur was designed to be built as a piloted, recoverable orbital spacecraft that would explore lifting re-entry and controllable landing capabilities.
The X-20 was the first aircraft, to my knowledge, in the world to implement the concept of manned orbital flight with lifting re-entry. In other words, controlled re-entry so you could land at a military base and have a reusable vehicle that could then fly again.
Although the program was canceled before the aircraft was built, the engineering phase yielded an enormous amount of complex data that would eventually be used to build a reusable orbital spacecraft.
As I mentioned earlier, the sharp lines, the delta wing lines, are based on the need to get high L over D, to get military flexibility of where we want to land. So we'd have a chance of landing 1,500 miles on one side to the other side, or 1,500 miles to the other side. We could also vary the longitudinal landing point. There were many different views on the program. This was in the early days of the space program. And this aircraft was a rather elegant way, sophisticated way of coming back in compared to the ballistic way. You didn't have to fish the guy out of the ocean. NASA saw a need for it. In fact, when it was terminated, Ray Blitzminghoff, who was then one of the deputy administrators of NASA, wrote a letter to the headquarters saying if the Air Force canceled the program, sooner or later NASA would have to restart it. And of course they did, shuttle.
In the early 1960s, the lifting bodies, blunt-shaped wingless vehicles, were developed for controllable atmospheric re-entry. Dale Reed, former NASA research engineer.
Several candidate shapes at the time that were under study. There was the half-cone, flat-top shapes that the NASA people at Moffett Field were promoting. There was the flat bottom, round-top shapes, which later evolved in the HL-10 at Langley Research Center. The flat-top shape was evolved in the M2. And so we selected the M2 as the first shape to do our first experiments with. And so we built our lightweight lifting body first, the M2, and then once we proved with this low-cost vehicle, which only cost about $20,000 for materials to build, we then were able to sell the idea of a supersonic version that was using rockets that we could launch from the B-52, much like the X airplanes.
Milt Thompson, first pilot of the M2 F1.
Obviously, these vehicles don't look like airplanes. There is a big question of whether or not they'll even get off the ground. And I think that's what we were really interested in building and flying the lightweight vehicle. We flew that vehicle for many flights back and forth across the lake bed. We had to acquire a hopped-up car to pull the vehicle fast enough to get it airborne. We had to get up to 75 knots to get it airborne, and ideally we wanted to get up around 110 knots. We were able to do this with this hopped-up car. Amazingly, that required something like 150 excess horsepower at 100 miles an hour to tow this vehicle. But we were able to get to those kinds of speeds. We then gained enough confidence to decide to take it up to altitude. And we utilized our C-47 to tow the vehicle on up to altitude and made our first free flight from altitude. And that was really a very significant flight. We were able to convince ourselves that the vehicle was flyable, it was maneuverable, it could be landed, and that answered almost all of our questions initially.
Bruce Peterson flew the M2F2 aluminum aircraft. On the 11th flight, the aircraft experienced severe lateral instability.
Well, the aircraft in our previous flights had exhibited some instability at lower angles of attack, and we didn't fully understand that. So my mission was to get some aerodynamic data after launch, and then the latter part of the flight to decrease the angle of attack to a lower angle of attack to see if the instability existed. We did that, everything went fine, and then about 17,000 feet to go, I started pushing over to gain speed to make my approach and push it over to a fairly low angle of attack. At that point in time, the nose slid out to one direction, immediately followed by a roll, and it coupled and got a very lateral, strong divergent lateral directional oscillation. The oscillations hit me across the head pretty smartly and dazed me. And I knew I had to recover wings level, because I was getting close to the ground. So I timed one of the oscillations and popped back on the stick and indeed did recover wings level. At that point in time, I looked ahead at me at my point of intended landing, and there was a helicopter hovering where I should be landing. So I told him to move west or get out of my way. And then I lit up the emergency solid rocket motor I had on board to give me a little more time. I went just behind the vehicle, didn't hit him, but either the rotor wash caught me or I got lower than I anticipated because I was off the marked runway. And I put the gear down, one gear door caught, and that flipped the vehicle, and that was the end of the ball game for the day.
Miraculously, Peterson survived the crash and has continued to make valuable contributions to aeronautical research. And the M2F2 was rebuilt and flown again as the M2F3. The rocket-powered Martin Marietta X-24A and X-24B represented the culmination of lifting body research in subsonic landing controllability. Al Draper.
The X-24B represents sort of a benchmark of the culmination of the high lift-to-drag ratio, lifting body work done at the Air Force Flight Dynamics Laboratory. It had tremendous benefits to the space shuttle in that it did develop this high aerodynamic efficiency, much more representative, if you will, generically to the space shuttle design than any of the other lifting bodies. And in its terminal maneuvering, if you will, supersonic down to landing, it essentially set the path for the highway down through the sky for the space shuttles.
On August 31st, 1987, Rockwell International was awarded a contract to build the X-31, an enhanced fighter maneuverability demonstrator aircraft. Sponsored by DARPA, the U.S. Naval Air Systems Command, and the German Federal Ministry of Defense, and developed by Rockwell and MBB in Germany, the X-31 is the first international aircraft in the X-plane series. Recognizing that close-in aerial combat will continue to be a necessary capability for future fighter aircraft, along with beyond visual range capabilities, the X-31 is the first aircraft to address post-stall maneuvering. Mike Robinson.
Post-stall maneuvering is the cornerstone of the EFM suite of capabilities, in that once you impart EFM capabilities into the airplane, you will tend to get the other capabilities without substantial additional penalty. It'll be a matter of just working out the details. So I'd like to describe a little bit of the detail of post-stall maneuvering, and to do that, I'd like to use the model and compare it to a more conventional maneuver, which is a high G maneuver of turning the airplane as tightly as you can in a coordinated turn to bring your nose back around to where you can point at an enemy who is somewhat behind you or perhaps behind you. In a post-stall maneuver, we don't use that high G, high acceleration type of turn. Instead, we pitch the airplane to a high attitude, yet start climbing such that the airplane is flying along a path as depicted by my finger. It continues to climb and pitch up to the point that you want to turn, then in essence rotates around the velocity vector with the nose coming back around. And by doing that, you can see that we have a much tighter, faster turn to bring our nose around and have a time advantage to get our nose on it, and therefore a firing solution against an enemy.
Building on the technology base generated by the HIMAT, Rockwell's remotely piloted high-G maneuvering vehicle, the X-31 will have a digitally integrated flight control system, carbon composite wings, and canards coupled with engine exhaust vectoring paddles.
There's another aspect of the X-31 program that's, if not unique, certainly very important, and that is that we've taken on a goal for ourselves, us and our partner MBB in West Germany, to build a very low-cost demonstrator. We have done some very unique things there, and you can do them on demonstrator airplanes, whereas you can on production. For instance, the basic assembly tooling on the airplane will become the frames, the major bulkheads within the airplane. A second thing, however, that we've done is a trend in modern industry, and it's something that could go to very highly used in a production-type airplane, too. And that's a fully computer-based master model of the airplane that's fully three-dimensional that will substitute itself for a mock-up, and that we can do fit checks and things that you would normally have to build a mock-up to do. As opposed to that, we're putting it right in the computer. You can see the fits, you can see interferences, you can move parts around and do all that, and then that database will go directly to the manufacturing people who will bend the tubes and put the equipment in per that computer-based mock-up. The next to the latest X-Series airplane, the X-29 and the X-31, are comparable in some sense in that they're both demonstrators of fighters. However, there's a very major difference. The X-29 was meant as a pure technology demonstrator to show new technologies, in particular the forward swept wing, but most certainly other things like high degrees of static instability, which are technologies and how they integrate into a fighter. Our X-31 airplane, on the other hand, is a capability demonstrator to provide those new tactical capabilities of enhanced fighter maneuverability to air combat crews. So we are not developing any new technologies per se. We're simply taking the very latest state-of-the-art technology and integrating them in a very unique way to provide this capability that we're talking about.
The first flight of the #1 X-31 is scheduled for the fall of 1989. And now to the future. The X-30, a pure technology demonstrator and precursor to the National Aerospace Plane, represents the most ambitious, complex, and expensive research aircraft program ever undertaken in the United States. The National Aerospace Plane Program is sponsored by the Air Force, the Navy, DARPA, the Strategic Defense Initiative Office, and NASA. Major airframe contractors during the current technology development phase are Rockwell, McDonnell Douglas, and General Dynamics, with engines being developed by Rocketdyne and Pratt & Whitney. Designed as a single stage-to-orbit vehicle, the X-30 will take off from a runway, cruise in the atmosphere between 80,000 and 150,000 feet at speeds up to Mach 25 and return to Earth at a runway of choice. Dr. Bart Barthelemy, Director of the National Aerospace Plane Program.
The National Aerospace Plane Program is a program to first develop a series of technologies which would allow the possibility of an aerospace vehicle, or an airplane that actually flies through the atmosphere and goes into space. And then following the development of these technologies to demonstrate that kind of a concept in an X-30, an X-vehicle demonstration program that would begin roughly in the early 90s and flight test in the middle 90s. That demonstration program would validate and make reasonable the data that we'll be obtaining from the development program and allow us then to go forward with the development of prototypes and conceptual vehicles beyond the X-30.
Powered by supersonic ramjet engines, scramjets, the X-30 may use liquid or slush hydrogen as a fuel. The X-30 will differ from previous hypersonic vehicles by using the available oxygen in the atmosphere as its oxidizer for fuel combustion. Integration of the propulsion system with the airframe, developing the lightweight yet super strength materials, and flight testing the vehicle presents major challenges to the program. Lieutenant Colonel Ted Wierzbanowski.
Specifically, the challenge of flight testing the propulsion system, it is going to be a very difficult problem. And the reason it's going to be a difficult problem is because when most people think of propulsion systems, they think of an engine like you see on the wing of a 707, okay? Well, that's not the case with the X-30. The propulsion system for the X-30 is actually the entire vehicle. We have to use the forebody of the vehicle to compress the air, sort of like a turbine does or a compressor does inside a jet engine. Then we have a little combustor section, which most people might think of as the engine, where the actual fuel is put in and combined with oxygen to get heat and thrust. And then we have the back end of the vehicle, which is really, in essence, half of a rocket nozzle if you really look at the vehicle.
Robert Gulcher.
The three basic material systems that are being developed, first is titanium aluminide metal materials, and the second one is a metal matrix composite, and the third one is the refractory composites, ceramics and things of that sort. As an example, this is one type of material structure that we use. This happens to be a titanium aluminide. This structure is made up of three sheets of titanium aluminide material. This top face sheet, the bottom, and then you see this wavy one in the middle. It's made up of those three sheets, and it's been expanded to give it very high strength at a very low weight. These types of materials will be developed much, much further, of course, along with the manufacturing processes and all that are necessary to carry these out. The metal matrix composite would be similar to this, except that in these face sheets you would actually see some very strong filaments that would actually strengthen this thing longitudinally to give it more strength. And then, of course, the refractory composites are ceramics, which can be like carbon-carbon, things of this sort that have been utilized in the past on shuttle, but again, there are advancements to this to give it more strength and lighter weight materials.
The tremendous challenges presented by the X-30 program go beyond new material technologies to include expanding the flight test envelope beyond Edwards Air Force Base in California to include continental North America.
The challenge of flight testing the X-30 in a sense of where we're going to flight test it is really a significant geometry problem. Because at the kinds of speeds that we're talking about flying, Mach 10, Mach 15, and beyond that, a Mach 15 turn, just a nice gentle turn, something that you might see in an airliner, will take you from the southern tip of Florida to Maine, just one turn.
Research in computational fluid dynamics, aided by the use of Cray supercomputers, is being conducted at NASA's Ames, Langley, and Lewis research centers. This has allowed prediction of aerodynamic data up to speeds of Mach 19, far beyond the capabilities of Mach 8 wind tunnels in operation today.
After we flight demonstrate the aerospace technologies with the X-30, we're looking forward to what we call NAS-derived vehicles, or aerospace planes that follow the X-30 demonstration program. And they'll be very exciting concepts. They'll be airplanes that will be able to get from any point on Earth to another point on Earth, any place, within about 2 hours. They could do this by flying through the atmosphere, or they could go directly into orbit and orbiting the Earth and coming down. And so it gives you the capability of delivering payloads or people or a presence from one part in the globe to another part in about a 2-hour time period.
The X-15, of course, was an aircraft that was launched from a B-52. It was not the kind designed, obviously, to take off from a runway. It was powered by rocket, used a lot of steel materials, things that, of course, were available. That was the early 60s, and those are the things that were available. To gain access to space with any kind of payloads, well, of course, the space shuttle was brought into being. It was basically an aluminum aircraft, but had the thermal protection system to be able to withstand the temperatures. It was launched then by very, very large rockets, both solids and the hydrogen-fueled rockets. And, of course, it leaves the atmosphere very rapidly and then, of course, goes into orbit. But it's very limited from the standpoint that it has to be at Kennedy or Vandenberg, perhaps, and it has to land, like at Edwards or at least very few places, as opposed to what the X-30 will do. The X-30 will not be limited from that standpoint. It'll be able to take off again from a conventional runway, utilize the air, the atmosphere for its oxidizer, go into orbit, and then be able to return and again land at any particular, convenient airfield. So we've gone clear from an airplane that launched a rocket airplane, and then we'll end up with actually being able to take off more like an airliner and go on into orbit under its own power and then return.